And welcome everyone to this webinar on the topic Sarus towards HPC performance for portable containers. This webinar is organized by CSCS, the NCC of Switzerland, in cooperation with EuroCC and Castile. And just to give a short idea, the webinar is intended to last roughly 1 hour. 45 minutes will be approximately time for the presentation, which also will be recorded. And after that, there's a Q&A session intended. In the interface of Zoom, you will find a Q&A button, which allows you to put in your questions also already during the presentation. And smaller ones we will reply immediately, and the bigger ones will be replied to at the end. And the two people presenting today, or one person presenting, is Alberto Madonna, who's software engineer and involved in the development of Sarus, and Theofilos Manitaras is answering and watching over the questions in the Q&A. He's a computational scientist at CSCS. With that, Roberto, I hand over to you.
Okay, thank you very much, Matthias. Thank you for the kind introduction. Good morning, everyone, also from my side. So today in this webinar, we are going to talk about Sarus, which is a container engine aiming to preserve the performance characteristics of the performance that is characteristic of HPC systems and supercomputers without compromising on the portability of container images. So this webinar is supported by the EuroCC and Castile project, and through them by the HPC joint undertaking. So we're very grateful for that support and for the visibility and opportunities that these projects enable for us and for the other centers for the other NCCs in Europe. So how do I want to structure this webinar? I will start with a brief overview of Sarus and talking a little bit about the architecture. Then I will highlight a couple of HPC-specific features that the engine implements. Then we go a bit more in detail, talking about the OCI hooks. Why are they so interesting, and what are the advantages of applying them to an HPC scenario? I will present you with some quick demos about how to get a standalone installation of Sarus, and to demonstrate the capability of Sarus and the hooks to customize containers on the fly regarding, for example, MPI and GPU usage. I will present some performance tests done with real-world applications, and then I will wrap up the presentations with some concluding remarks. So what is Sarus in a nutshell? So Sarus is a container engine, so a piece of software that receives user input, user requests, pulls container images from a remote registry or from local files, and from the point of view of an end user, runs a container. Sarus has been designed for the requirements of HPC, like multi-tenant system with several concurrent users, in the presence of workload managers, parallel file systems, and so on. It proposes a consistent user experience with Docker, so it has a similar look and feel to Docker, so that users do not have to learn a new tool from scratch. And it creates containers which are capable of achieving native performance in a way that is completely transparent to end users through the extensions provided by OCI Hooks. Sarus implements a modular design which is based on open standards, so that third-party upstream components can be used on HPC systems as well, even if those components were not originally conceived for HPC, but for example, they could be originally meant for the cloud or enterprise computing. This modular architecture also can easily accommodate new extensions, which may come from community peers or vendors. So in this slide, we see represented a typical user workflow that we see at CSCS for containers. Users start with creating a Docker image in their personal workstations or laptop. Then they push that image to a remote registry like Docker Hub. And then the image is pulled into the storage at the HPC center and then finally deployed at scale on the computing system. And within this process, Sarus can carry out steps 3 and 4, so the pull and the deployment at scale. Here we see a diagram representing a high-level overview of the architecture of Sarus. So on the left side of the slide, we see that Sarus interacts with users, Docker registries, input and configurations file, parallel file systems. So all the entities that we would expect present to carry out the functions of a container engine. So nothing really surprising on this side. The right side of the slide is more interesting because here we see that Sarus is not directly responsible of creating a container process, but rather it delegates the creation of the container to a lower level runtime program. This interaction with a runtime is not something that is custom or specific to Sarus, but follows the industry standards defined by the Open Container Initiative, or OCI. In this way, a third-party runtime program adopting the same interface, following the same standards, can be used to deal with the low-level details of spawning a container process, while Sarus takes care of the HPC-specific aspects. Sarus currently uses runC, which is a reference implementation, which is also at the heart of Docker, is the internal runtime of Docker. One of the fundamental design points of Sarus is the capability of configuring external programs, which are called by the runtime, to perform additional actions on the container. These programs, which are represented as the green boxes in the diagram, also use an interface defined by the OCI. And for this reason, they are generally known as OCI hooks. I will be going in more detail talking about OCI hooks in a short while. But for now, I just wanted to highlight a couple of HPC-specific features that Sarus brings to the table. So the first one is about exposing the PMI2 interface inside containers. So PMI2 is an interface that is adopted by some MPI implementations, like, for example, MPitch and its derivatives, to communicate between the processes. The interface is composed of a set of environment variables and Unix sockets, which are exposed as file descriptors. There are a couple of things to pay attention to when using this interface and wanting to expose it into containers. So, for example, the PMI2 processes on the same physical node will communicate through a common dev sham. And if we want to leverage runC's file descriptor preservation, it requires a contiguous set of file descriptors. And even then, when we get into the container, the file descriptor numbers are not guaranteed to be the same as they were on the host. So in order to facilitate this process and importing and exposing the PMI2 interface to containers, Sarus manipulates the file descriptors as needed to create a set that is optimal for the runtime to be imported into the container. And Sarus also realigns the environment variables to use the actual new file descriptor values that there will be into the container. And finally, the dev sham file system is bind mounted from the host so all the containers on the same physical node can seamlessly communicate between them. The second features is about the integration of the CUDA environment. So NVIDIA provides a program called the NVIDIA Container Toolkit to expose GPUs within containers. And the actions of this toolkit are controlled through an environment variable called NVIDIA Visible Devices. This variable is already present in the official Docker images provided by NVIDIA, so the official NVIDIA CUDA images. And it is already set to expose all available GPUs into the container. However, some workload managers, for example, Slurm, when using the generic resource scheduling plugin, already allocate GPU devices to the jobs on their own and set the according environment variables. So if the settings of the workload manager and the NVIDIA toolkit are not aligned, there is the risk of, especially in multi-GPU systems, of exposing into the container a different or additional devices than those which were allocated by the workload manager. Additionally, when we get into the container, the GPU IDs are reset, and this can potentially hamper the capability of applications in the containers to use the GPUs because they're looking for a different ID. So Sarus instructs the NVIDIA Container Toolkit to honor the allocation of the workload manager and also adjusts the CUDA Visible Devices environment variable so that applications in the container can actually use the correct GPUs that are present inside that. These modifications happen without any intervention required from the end user and represent an alternative approach compared with the GPU support CLI introduced by Docker starting with version 1903. So I have already mentioned before about the central role that hooks play in the Sarus architecture and that they bring great advantages. So it is worth to spend a little bit more time to go into detail and understand more what I mean with those statements. So first of all, what is the OCI? So the OCI stands for Open Container Initiative, which defines itself as an open governance structure for creating open industry standards around container formats and runtimes. Essentially, it is a group formed by key players in the container industry, and like, for example, Docker, Red Hat, Amazon, Google, Microsoft, all the heavy hitters are there, basically. And part of the runtime specifications defined by the OCI outline an interface to plug in or hook external programs at certain points in the lifetime of the container. So in the bottom part of the slide, you see a graphical representation of the life cycle of a container from creation to destruction. And the blue rings exemplify different points in which programs can be hooked, can be executed to perform additional actions. And as you can see, these programs can be any kind of executable. Like there can be a binary program, it can be a shell script. So there is a lot of flexibility here. The interesting thing is that these hooks can customize the container. Why is this interesting, especially for us? But because when we deal with containers in HP and HPC, in reality, we are facing a contrast. Because on one hand, best practices and standards tell us that images should be as portable and self-sufficient as possible. And on their part, container images often use commodity or off-the-shelf software. On the other hand, what characterizes HPC are custom technologies, both hardware and software. These technologies are often proprietary, sometimes even machine-specific in a sense. So once we get these portable container images on the systems, we need something to provide this missing link to cover the last mile and be sure to bestow performance to the portable images. And the hooks enable us to do just that by customizing container file system and injecting native host resources like interconnect-aware MPI libraries, network devices, drivers. So the image remains portable, but the container process runs with native performance because it has access to the native hardware. From the point of view of a system administrator, hooks are interesting because they allow another level of control to the installation of container runtimes and container engines, because hooks can be selectively configured to only enable specific features of this that are available or desired from a specific system. So they can better map the installation of the hardware features into the container. From the point of view of the user, this means that the same image can be reused throughout the whole life cycle of an application or a research or a project. For example, going from early evaluations from an early prototype on a laptop with Docker to evaluation runs in a small cluster and up to full production runs in a supercomputer with even more exotic hardware, all the while leveraging the different characteristic of each system and leveraging them at the full of their potential. From a software development point of view, hooks enable separation of concerns. So on one hand, the developers of container tools like engines and runtimes do not need to integrate or reverse engineer support for complex technologies. On the other hand, vendors and technology specialists can develop feature-specific extensions without having to know the details about container creation. The point of contact between these two groups is the OCI interface. So a common ground which is broadly adopted all through throughout many realms of computing. The end result is that HPC technologies can be made available sooner with a lower development effort and followed by the respective experts. So this is a list of hooks that we are using at CSCS in a production scenario. We use the NVIDIA Container Toolkit for GPU support. We have an MPIC-based MPI Hook to get native performance from host MPI libraries. We have a glibc hook to ensure that resources mounted from the host keep working also with images based on older Linux distributions. We have an SSH hook for connections. We have a Slurm synchronization hook, and finally a timestamp hook for profiling purposes. In this list, the two most interesting hooks are the MPI Hook and the NVIDIA Container Toolkit. So I'm going to focus a little bit more on those two. So the MPI Hook is able to replace the container MPI with native libraries at runtime, and thus achieving the full performance of the system interconnect. In order to seamlessly perform this replacement, the hook relies on the ABI compatibility initiative defined by the MPIC organization. all these operations happen in a way that is completely transparent to the users and only require a command line option to the Sarus run command, which, as you can see in the slide, is --MPI. In the bottom part of the slides, we see the results for an all-to-all MPI latency test for a variety of message sizes. We have container data in red and the corresponding native application in blue. And we're running between 2 and 128 nodes. And you can see that the performance profile between container and native is very close, and it's very consistent throughout node counts and message sizes. Coming over to the NVIDIA Container Toolkit, this toolkit is an open source software provided by NVIDIA, which is able to import the drivers and the GPU device files into the container. So the container gets access to the native hardware. And as I said, with Sarus, this happens without any specific input necessary from the user side. The NVIDIA Container Toolkit is also the first example of a vendor hook to be successfully tested and used on our flagship system, PITS Dyned. And here in the bottom, you see a table representing a results comparison for an n-body sample from the CUDA SDK. If you are wondering how these hooks can be configured, this is an example of the JSON file that Sarus requires you to create. So, for example, in the case of the NVIDIA Container Toolkit, once you get the NVIDIA software, you just have to write a file like this one. This example is about 15 lines of JSON, and then you basically that's all that is needed from Sarus to start creating GPU-enabled containers. And also in our documentation, which we have more examples of how to configure and use the other hooks that I mentioned before. Okay, so I think it's time to get a little bit more on the practical side, and I will show how to perform a standalone installation of Sarus on a virtual machine. Let me fetch the video. Okay, so here we are on a Debian Buster virtual machine, just for our example purposes. The first thing that is required by Sarus is the SquashFS tools package, because they are used for image importing and also for setting up the base file systems for images. So I check if that's available. The SquashFS tools are not available, so I very quickly proceeded to install them with the package manager. And these tools are, of course, available from the, as I said, from the SquashFS-tools package. We do another check. And now make SquashFS is there, so all set. We are ready to get over to the installation of Sarus itself. So in order to do this installation, I am going to download from GitHub what we call the Sarus standalone package, which is a self-sufficient statically compiled version of Sarus, with also bundling the hooks and other dependency programs. In this example, I'm retrieving version 132, but basically just changing the version in the address you can get any version that is available from our GitHub repository. So I create the installation directory that I will place in /opt. I just untar the archive in the installation directory. Then after the files are available, I need to call a configuration script to basically initialize the installation and creating a minimal starting configuration for Sarus, which will be able to bootstrap essentially it will enable the engine to perform the most specific commands. It does not enable all the possible features of Sarus, but sorry, it just allows you to get started. So if you want to further enable additional features, we have a full documentation, and then you have to provide to customize your configuration file. So this is the configuration script running. After it is done, we just need to expose the Sarus binary in the path. We can, as the output is saying, we can just export an extension to path, or like I am doing here, we can just append the new value of the path through the bashrc file. So I source the bashrc, and let's verify that we can correctly access Sarus. There it is. This is the help message when no commands are provided. The very last thing before we can start using Sarus is making sure that the kernel modules are, that the required kernel modules are enabled. So, and these one are the loop, the squashfs, and the overlay fs kernel modules. And once I have done that, I can, for example, proceed to pull an image. So I'm going to pull Alpine, the official image for Alpine Linux from Docker Hub. Alpine is a minimal Linux distribution. It's very, very lightweight. It's good for quick tests. And when the image is retrieved, I can run it with the Sarus run command. And just for the sake of this example, I'm asking to print the informations relative to the Linux distribution. And we see that actually we get an Alpine Linux container within our Debian Buster VM. So this is a way we can perform a quick and standalone installation of Sarus. Let's go back to the presentation. The second demo I have prepared for you is about container customization and enabling GPI and MPU support. MPI and GPU support into in containers. So let's go to this other example. This set of examples has been performed on PITSDyned, so our Cray XC50 supercomputer at CSCS. And the examples that I'm going to show you use the OZU micro benchmarks, which are a suite of small programs to evaluate the performance of MPI implementations and network hardware. I am going to use an image created with this Docker file that you can see. The image is based upon the official NVIDIA CUDA image for CentOS 8. So I just install a few compilation tools. I download and compile MPICH 314 and the OZU microbenchmarks 5.7 from source. And when configuring the OZU microbenchmarks, I also enable CUDA integration. And finally, I define a custom working directory for convenience when working with the image and the containers. Okay, so I have already pulled the image on PITSDINT, so the image is already available, and I have already obtained an allocation from Slurm, so I can already go on and call Sarus run, followed by the image name. So is the same syntax that you would use for Docker, for example. And as you can see, the image name just indicates the most important piece of software in the image, like the versions of the micro benchmarks of the MPICH and CUDA libraries. And I am going to use the OZU latency program, which is a small program performing a series of ping-pong communication between two processes and reporting the latencies of those communications for a variety of message sizes. So with this command, I am basically running the image contents as they are. So can I launch this program right now? Well, not quite, because the workload manager, the Slurm workload manager on PITSDINT, by default uses an MPI launcher communicating with a Cray-specific interface. And the vanilla MPICH libraries into the image are not able to understand such interface. By default, they would use the more widely diffused PMI2 interface. So one way that I can still run the image as it is by instructing the host workload manager to not use the Cray PMI interface, but to use the PMI2 interface. And I can do so with the --MPI equals PMI2 option to srun. So in this way, the MPI launcher from the host and the container and the MPI libraries in the container will speak the same language and will be able to understand each other. So I launch the command, and the results start trickling in. So these are the numbers that we get when we are running the container as it is, with the original software stack from the image, which as you can see, it's based on CentOS and on basically commodity software. But this image uses MPICH 314, which is ABI compatible with the native libraries provided by Cray for the specific system. So I can use Sarus and the MPI hook to replace the original libraries in the image with the native MPI implementation provided by Cray, which will be able to use the Areas interconnect on PITSDINT to its full potential. So in order to do that, I use the --MPI option to Sarus run. Now that I'm going to have the Cray libraries into the container, those are going to understand naturally the default Cray PMI interface used by the launcher. So I do not need the PMI2 option from srun anymore. Now I launch the containers again. And these are the results. And as you can see, the difference in performance is is quite noticeable, and the latencies are greatly reduced. But the advantages of having the native MPI implementation inside the container do not stop just at performance. For example, we might have access to additional features which were not available in the original MPI, in the original MPI libraries of the image. For example, we might perform our direct RDMA between GPU devices using the NVIDIA GPU Direct technology. In order to do that on PITSDINT, first I need to define an environment variable, which is called MPICH RDMA enabled CUDA, and set it to the value of 1. The second thing that I have to do is to add a utility program to the arguments that are going to be executed into the container. I would like to point out that this get local rank utility program is not a requirement of Sarus or PITSDINT or anything. Is just required by the way the OZU benchmarks programs are implemented. So finally, I specify OZU latency that I want to use the CUDA transport, and that I want to perform a device-to-device transfer, a device-to-device communication. Launch the containers again. Just wait a little bit. Oh, sorry. That wasn't me. Okay, and we finally see the results. So we can see from the graphical output that we are indeed running an MPI and CUDA program. So the GPUs are available inside the container, and then we are performing a device-to-device transfer of data directly. And these are the level of latency that the OZU program has recorded. So we just saw the flexibility that Sarus gives us when running containers with MPI. So we can run either with the original software stack from the image, or we can inject the native MPI and also add GPU devices on top of that. So it's basically up to the choice of whatever we want to do with our workflow and with the images that we run. So the final thing that I want to show you today is is a set of real-world application tests which compare the performance between native and containerized versions of the same applications, so that we have a more complete view of the capabilities and results that we can get with Sarus outside of very specific and synthetic essential benchmarks. So the first application I want to show you is GROMACS, so an implementation of classical molecular dynamics simulations. The test case is the test case B from the PRAISE Unified European Applications Benchmark Suites. Container data is in red, native data is in blue, once again, and we are running from 4 up to 256 nodes. Once again, we see that the results from between the container and the native applications are pretty close, with the container application even inching slightly ahead at the higher node counts. Then we have a combination of TensorFlow and Horovod performing the training of a convolutional neural network from TensorFlow's own benchmark scripts. The network is ResNet 50, being trained over synthetic ImageNet data. And we're running between 2 and 1,024 nodes. And again, we see a very, very close, very, very consistent performance profile between the native and container applications. The final example, the final set of results is from COSMO, so a numerical weather prediction software used by several national weather forecasting services for operational forecasts and daily forecasts. The test case is a near global idealized baroclinic wave, and this specific plot, we see the results of the weak scalability test running up to 2003 and over 2,300 nodes, basically 2,336 nodes. The two data series correspond to a different number of grid points per node. And we can see that both data series are quite, the lines are quite flat. So what we would like to see on a good weak scalability test, and once again, container native results being trailing each other pretty closely. I think that here in this test we are within 1% of absolute difference between the numbers. So in conclusion, Sarus is a container engine for HPC compliant with open standards. It aims to combine the portability of containers with the native HPC performance. In order to do so, it integrates with HPC infrastructure and software on one side, and on the other side, it customizes containers at runtime with standard plugins. On top of that, Sarus provides a Docker-like command line interface for convenience of use and a familiar user experience. So this is pretty much, If you're interested in knowing more about Sarus, the code is open sourced on GitHub. We have a full documentation on Read the Docs. And you can, if you're interested in contacting the Sarus team or the NCC Switzerland team regarding Sarus, we have an email address, which is sarus@cscs.ch. And if you're interested in a more formal introduction to Sarus, in 2019, we published a peer-reviewed paper in a workshop tied to the ISC conference. So this is pretty much everything that I wanted to show you today. I hope you find this presentation interesting, and I thank you very, very much for your attention.